Okay. So actually quite a lot of ground to cover. We're a little behind. And the next exam is a week from today. We need to get through chapter 13 on the outer planets. So we're sort of only about halfway through chapter 11 right now on Jupiter. But anyway, okay, so we'll go ahead and finish up on Jupiter towards the on. So just to review a little bit, again, the unusual thing about Jupiter compared to the terrestrial planets we looked at is this first example of a gaseous planet, not a rocky planet like the terrestrials are. And it has a pretty low density, as you'd expect for something that's made out of gas. The outer layer here is molecular hydrogen, which is H2 gas, and that can exist under earthly conditions as well as out there on Jupiter. But when you go deeper into the planet, we achieve higher temperatures and pressures, and we start to see a new phase of hydrogen called metallic hydrogen, which actually does not exist under earthly conditions. And this particular phase, we'll see, is going to play a role in the production of the magnetic field of Jupiter. Because remember, the two ingredients you need for the magnetic field is pretty rapid spin, so you can get circulation, and you need to have an electrically conducting fluid of iron. So on Earth, it's nickel iron. On Jupiter, it's a gaseous planet with a rocky core. There's not much iron, so this electrical current is not going to be in the form of circulating iron. But you notice this hydrogen is called metallic hydrogen. It has the capability to have free electrons moving around, just like a metallic conductor would, like iron or copper or something like that. So this metallic hydrogen is going to turn out to be the material which is actually able to do this circulation I was talking about and achieve the currents necessary for magnetic field production. And again, the interior of the rocky core, really kind of more of a molten kind of rocky core, because if you look at the temperatures of the core, pretty high, 40,000 kelvins and 50 million times Earth's atmospheric pressure. And that's also a bit larger than the Earth, that core. All right, so let's move on and talk about the moons a little bit. When we look at Jupiter through a small telescope, we see the 4 moons known as the Galilean moons, because those are the 4 moons that were actually observed by Galileo with a small, modest-sized tracker telescope, which was all you could afford at the Italian Walmart that was available at the time there. For a larger telescope, so he got a small telescope, but amazingly he saw these 4 dots moving around Jupiter. And remember, the significance of this in the history of astronomy was that it revealed that there was at least one other center of motion other than the Earth, because he actually saw that these things were certainly orbiting around Jupiter. You can see motion on a daily basis. So that was the significance in the history of astronomy. Now, the 4 major moons of Jupiter are these Galilean moons, the innermost moons, also the largest moons, and that's the reason he discovered them, because they're the largest moons, the brightest ones. Now, if we look at distance from Jupiter, the innermost one is Io at 422,000 kilometers. Now, remember that the moon is around 350,000 kilometers out from Earth. So this is a little bit farther out from Jupiter than our moon is from us, but it's sort of comparable. Then we go to larger distances, Europa, Ganymede, Callisto. And what we're going to see as we look at these moons is going to be another instance of this idea of differentiation. So I'm kind of previewing a little bit here. But Jupiter was very hot during its formation, and consequently icy materials became volatile and evaporated in the moons that were closest to Jupiter. But the more distant moons, like Callisto and Ganymede, are more icy. So you see kind of an example of the same kind of differentiation I've been talking about in the solar system, operating in this sort of mini system around Jupiter. So the purpose of this is basically just to contrast the major moons of Jupiter. Again, the Galilean moons. There was the Io, which is that innermost moon, almost exactly the same size as our moon. Pretty near the same density, too, because there's not really a lot of ice on Io, as it turns out. As we move out to Europa and Ganymede and Callisto, you notice that they're all sort of comparable size to the moon and Mercury, but they look different as we move farther out. And we're going to see that that's due to the presence of more ice on these moons as we move out to Jupiter. And the ice can be blackened by high energy radiation over time, so we can see this kind of pockmarked blackish surface. And then we'll be talking about Saturn later on today, and that's the primary moon of Saturn is Titan, which is fascinating because it actually has an atmosphere. All right, so there's actually dozens of moons orbiting around Jupiter. There's actually upwards of around 60 moons if you actually add them all up. So these Galilean moons, again, are the primary ones. And as you might expect, due to the proximity to Jupiter, they are, for the most part, in synchronous orbits, meaning what that really means here is tidally locked orbits, just like the way the moon is in a tidally locked orbit around the Earth. Yes? Any heat to its moons?
Yes.
Right. Well, okay, so the situation right now is that Jupiter's cloud top temperature is only about 125 kelvins. Okay? Now the thing is, that's actually a little hotter than what you'd expect at Jupiter's distance from the Sun. The equilibrium temperature at Jupiter's distance from the Sun is only 105 kelvins. So we talked about this a little bit last time, how Jupiter seems to be radiating some of its heat of formation still, so it hasn't equilibrated yet. It's a little warmer than it will be, say, in a billion years or so when it's cooled off. But, to more directly answer your question, that cloud top temperature of 125 kelvin is way too low. You know, it's super, super below freezing, so it wouldn't have any influence today on the Galilean moons. But historically, again, billions of years ago, Jupiter was much hotter. And that's when it would have, you know, caused melting in the innermost moons like Io, and that's why they don't have any ice. So that's kind of a historical process that took place. But anyway, okay, so remember that the Earth's moon is in synchronous orbit. It's a tidally locked orbit. So Jupiter is 318 times the mass of Earth, and Io is roughly the same distance from Jupiter that the moon is. So, you know, if we're going to have tidally locked orbits around the Earth, you know, you'd think that with Jupiter's incredibly strong gravitational field, you would also have tidally locked orbits. And we do that, see that for the most part. The outer three Galilean moons, ironically, are the ones that actually are in tidally locked orbits. It turns out that Io isn't quite in a tidally locked orbit because of a kind of a curious gravitational phenomenon. Now that's, of course, that is surprising because Io is the innermost moon. So you'd think that if any of the four were going to be tidally locked, it actually would be Io, right? But what we're going to see is there's actually a gravitational influence from the next moon out, which is kind of interfering with Io's tendency to settle into a tidally locked orbit. Okay, so we sort of think of this as kind of a mini solar system, quote unquote. I mean, you know, Jupiter's not a star, so it's not really a solar system, but it is kind of a group of bodies that are obeying a version of Kepler's third law, which would be the version we would write down for Jupiter, with Jupiter's mass. And to pick up on a theme I mentioned before, as we move out away from Jupiter, we see decreasing density, which again is this concept of differentiation. This is a shot taken by Voyager as it was cruising by Jupiter, and you can actually just happen to see Io and Europa against Jupiter. So this is certainly a monster, huge planet. I mean, this is 10 times the size of Earth, 10 or 11 times the size of Earth. So if you want to think of it, let's see, if we replace the moon with Jupiter, let's think about how big Jupiter would appear to be. Well, let's see. The moon is about a quarter the size of the Earth, and Jupiter is about 11 times larger than the Earth. So if you do the math, if you replace the moon with Jupiter at the same distance, it would be 44 times larger than the full moon that we're seeing. Now remember that the Earth-Moon distance is actually similar to the distance between Io and Jupiter. So the bottom line is that if we were on Io and we were looking at Jupiter in the sky, it would look, you know, about 40 times larger than the full moon looks. So, you know, indeed, it would be, you know, incredibly dominant feature in our sky if we were working around at that distance from Jupiter. All right, so to get back into this idea of density, when we pick up the density, we look at Io moving out to Callisto. Starting with Io, we see a density which is actually similar to the lunar density or the Martian density. And so we look at Io, and it looks like a body that's probably rather silicate in composition, maybe with a little bit of iron, but not too much iron, because of course the density would be a lot higher if there was a lot of iron, just as we've seen when we discussed the terrestrial planets. But there's a definite trend here of declining density as we move out. And we don't see the differences here, but we talked about this a little bit already. The masses are actually all pretty comparable to the mass of the moon. But what we're seeing reflected in these density figures is an increase in the ice composition as we move out away from Jupiter. So, as I tabulate here, Io, there is some iron, a lot of rock. As we move out to Europa, it gets icier. with some rock mixed in. Ganymede is a little sort of more ice, and then Callisto is similar to the amount of ice that's in Ganymede. Now, we can even go a little further with this idea of differentiation, because if we think of each of these individual moons, and we ask what has their life history been, well, the ones that are closest to Jupiter, like Io, would be expected to have participated in a tremendous amount of melting because of the heat that's associated with Jupiter. So we would expect Io itself actually to be fully differentiated, perhaps with some minor amount of iron sulfide core or something like that. When we move out to Europa, at a larger distance from Jupiter, it is actually probably differentiated with some ice around the surface due to refreezing at the distance that it is. But when we get out as far as Callisto, we're seeing an object here which is pretty much primordial. In other words, it was far enough from Jupiter so that even when Jupiter is very hot and radiating thousands of degrees of, thousands of kelvins rather than just 125 kelvins 15 out, it was at enough of a distance that it didn't melt completely. And consequently, what we see in Callisto is kind of this dirty snowball mixture of rock and ice, a homogeneous mixture on the inside. So the bottom line is that Callisto itself is not differentiated because it's still got its primordial structure, having not really melted. So this is just a figure from the book that kind of follows up on that idea. We just look at Callisto here. This is the point I was trying to make, that we believe Callisto is a pretty homogeneous mixture of ice and rock. If we took Callisto and moved it, if it had lived closer to Jupiter, it would have heated up enough to become differentiated. But at its distance, it didn't heat up enough to differentiate. So we're seeing basically a sort of a primordial composition there. Maybe not so different from a cometary composition, actually, if we start talking about comets later on. Conversely, when we move into Io, we do see some iron. Not a lot of ice, but a lot of rock there. And again, we see an increasing amount of ice as we move out. But Callisto is the first one that's so far out, it's not differentiated. So we see, again, this theme of differentiation in multiple different occurrences through the course.